Okay, so here on page 48, we're actually going to jump sort of towards the middle. This is going to be a quick thing that will reiterate something we talked about last time. Take a look at this function here, f of x equals x squared minus 9 over x plus 3. We're going to graph this thing in a second. Before we do, we're going to rewrite it because of the top factors. So go ahead and take a moment to factor the top. So how does this one factor? X plus 3, x minus 3, right? That's a difference of 2 squares. It's okay if you did not factor it as quickly as that. As long as you can factor it in your own time, that's fine. And what nice thing happens here? They cancel, x plus 3 and x plus 3. So downstairs there's a 1 remaining, which we don't actually need to write. So really this is just x minus 3. Yeah? And with your arm, can you show me what the graph of f of x equals x minus 3 looks like? X minus 3. X minus 3 is a line. You can use one arm or two. It is an uphill line, right? Not terribly steep. Slope is 1. So we're just going to graph that uphill line. I'll start with the y-intercept. What is it? It's negative 3. So that'll be the first point that I plot, minus 3. And then the slope of this line is 1. So that means you go over 1, up 1, over 1, up 1. I'll just plot a couple more points here. That's enough for me. And then with a straight edge or freehand, just connect the dots. It's harder than it looks. All right, that's close enough. Okay, so there's the graph, except it's not quite the graph because this wasn't quite x minus 3. That's not what it started as, right? It started as that fraction, that rational function up there. And so even though, yeah, we canceled, and even though we just got x minus 3, there is a slight difference between the graph that we have drawn and the graph of the original. And we talked about this last time. But looking at the original, what is the one excluded value of x? Negative 3, because that would involve dividing by 0, which is a problem. So at x equals negative 3, we cannot do this original function. So how does that appear in the graph? Yeah, so at x equals negative 3, we don't get to put the dot right there, negative 3. We need to erase that dot and replace it with a whole open circle. And it's not enough to just sort of arbitrarily slap that open circle down. I really want you to know the exact coordinates. The x is easy. What's the bad x? Negative 3. No problem there. The y is more challenging until you see the process. It's challenging because if you try plugging negative 3 in for x here, what do you get? You get a 0 in the bottom, and I'm stuck as soon as I get a 0 in the bottom. And so I can't plug negative 3 in there, but where can I plug negative 3? Is at the end, after you've reduced. There's nothing stopping you from plugging in, just a c. So if you plug negative 3 in here for x, what do you get? Negative 6. That's the y coordinate, right? So that's this guy, negative 3 minus 3, which is negative 6. Okay. So we talked a little bit about holes last time. Here it is again. Holes appear. Why did a hole appear in this problem? We couldn't include it, but what made this hole appear? Yeah, it was an excluded domain, but let me give you another function here. Let's look at this guy too. X plus 4, x minus 3, x plus 3. I've only made one small change. Yeah, that's true. You guys see the one small change, right? It was x plus 3. I just changed it to x plus 4. Which means that I can't do what that we did over here. We can't cancel. So we can't do anything. Now, what's the excluded value of this new function? It is still -3, right? So I'm just going to put x cannot equal -3. Does that mean there's a hole on this guy at -3? There's actually something far worse than a hole on this one at -3. Yeah, we just can't do anything at -3. And do you guys remember we plugged in, we had this big table last class where we plugged in numbers near the excluded values. We plugged them in because I can't plug -3, but I could plug -2.999, right? Or -3.001. And when we plug in numbers like that, we start getting output values, y values like 100 and 1,000 and 1,000,000. And so what did that mean about the original function if we're getting like 100 and 1,000 and 1,000,000? What's going on at x equals -3? So 100, yeah, like we're getting really close to -3 horizontally, but the output could be like 100 or 1,000 or 1,000,000, and it's going really, really high. And what did we call that? It was an asymptote, right? This is stuff that you guys filled in the activity last time. If it said find the vertical asymptote, you just look at the bottom and say, oh, -3, right? It's the excluded value. And so in addition to us understanding how to graph a hole, where to graph a hole, I want us to understand what is it that makes something a hole from the denominator versus making something a vertical asymptote. So here's our answer over here. This is a vertical asymptote at x equals -3. So here's our conclusion. If you have an excluded value from that denominator, it's either going to be a hole or an asymptote. Those are the only two choices. What made it so that the first guy was a hole and the second guy was an asymptote? Right, in the first one, we were able to eliminate that denominator. We just canceled and the denominator, poof, vanished. And so if the denominator completely vanishes, what do you have? You have a hole. But if the denominator is still there, that is a far more fundamental problem. And what does that give you in a graph? It's an asymptote. Right? So one of them is like a really big problem. That's the asymptote. X plus 3 still in the denominator. And the other one, little problem. Small blip in the graph. So we can play games like, I can give you something. I'll just make this up here. Equals x plus 4 squared, x minus 3 to the 8th. Let's do an x plus 2 right there. Divided by, go ahead and copy this guy for me. So I'm going to put over here a x plus 2 to the 5th, and then x minus 3, let's do to the 6th, and x plus 4 to the 3rd. Okay, so let's figure out what the excluded values are. We can do that by looking only at the denominator right now. What are they? -2, +3, -4. Just looking at the factors on the bottom and making them individually equal to 0. Good? Okay. But now we start to cancel some things. So what about the x plus 4s? How many are left and where? 1 at the bottom, right? So there's one more down here. So this guy cancels entirely, and I'm going to replace this with a 1. And what about the x minus 3s? How many? And 2 left over where? On the top, because there's more up there. So all the ones on the bottom go away, and we got 2 of them left. And then finally, x plus 2s. 4 on the bottom goes away on top, right? So anything still left in the bottom is a problem that is too difficult to resolve. Still fundamental problems if they are still downstairs. So what is going on at x equals -2? Is it a hole or a vertical asymptote? That is a vertical asymptote. It's a problem we cannot fix. What is going on at x equals -4? It is a vertical asymptote We cannot fix that. What about at x minus 3? That one's a hole. Wasn't really a problem. Wasn't really there. Small issue, small blip in the graph. Okay? So this is our conclusion. That example hopefully gives us all the cases, right? Like you write your excluded values first before you cancel anything. Some of those excluded values will be holes if they really disappear from the bottom. Some of them will be more fundamental issues. Those are the asymptotes that stick around in the bottom. All right? Okay, so let's move on to the next page. And we're going to talk about end behavior for these horizontal asymptotes. Let's take a look at part A. So the function in part A is 9x squared over the quantity 3x squared plus 1. Look at the graph. This is just a screenshot from a graphing calculator. What does it look like is happening as x goes to infinity? What's happening to the f of x values? Looks like we're approaching 3, right? We're a little under 3, but it sure looks like it's almost becoming horizontal there. So we can put that right there. As x goes to positive infinity, far right, the y values look like they are leveling off at 3. I know that, like, if you just look at pixels, it appears that it's flat exactly at 3. But that's just a graphical thing. It never actually gets to 3. Maybe it's 2.999. Maybe it's 2 and then 1800 nines, but it will never be exactly 3. How about as x goes to minus infinity? Yeah, that means going to the far left. And again, it's 3. In the next picture, different formula, different graph. As x goes to infinity, what about the f of x values? Looks like it's 0, getting closer and closer to 0. And as x goes to minus infinity, also 0. And it turns out anytime you have a horizontal asymptote for a rational function, there can only be one. It's got to be the same number in both of those blanks. If one side is going to 3, so is the other side. That isn't the case in this last picture. As x goes to infinity to the far right, what happens to the y's? Infinity here. And then as x goes to minus infinity, is negative infinity there. Okay, so let's write down our conclusions here. What is the equation of the horizontal asymptote for this one? It's this, I'll draw it dotted. That horizontal line is, give me an equation, y equals, right? Every horizontal is a y equals. So y equals 3 there. For the next one is y equals 0. And the last one, is there a horizontal asymptote for this last one? No, so that's an okay answer. No horizontal asymptote. So answering those questions was pretty darn easy because we were fortunate enough to have screenshots. But building the screenshots, like graphing these things from scratch, is really hard. So wouldn't it be lovely if we could come up with those same answers, but just using the formulas, right? The formulas are up above. So here we go. If you take a look at this original guy right here, part A, when we send x to infinity, like x is becoming really big, right? Think about the denominator, 3x squared plus 1. So I'm just gonna pick a few big x's. So maybe x is 100. So it's 3 times 100 squared plus 1. Maybe x is 1,000. You don't need to write this part, right? X could be 1,000,000. We just keep picking bigger and bigger x's. Would you agree that that plus 1 is pretty insignificant when x is big? Like 100 squared is 10,000. And so that top number is how much? It's 30,001, which is not that different from 30,000, right? And it's even more in the next one. 1,000 squared is 1,000,000. So what is that bottom number? 3,000,001. Really, like in the grand scheme of things, that plus 1 is not going to have much impact. Agree? And so because we are picking numbers that are really, really big, I'm going to do something that isn't mathematically allowed, but hopefully you'll bear with me. The plus 1 doesn't matter if x is huge. If you plug in x equals like, I don't know, 0.3, sure, the plus 1 is going to have a big difference. But if you're plugging in x equals 1,000,000, plus 1 hardly matters at all. So if you allow me to just disregard that plus 1, what does this thing reduce to? 3, right? X squareds cancel. 9 over 3 reduces to 3. Why are we really excited that 3 is the output? Because that's the equation of the horizontal asymptote, right? That's how we see it, is we ignore the stuff that doesn't matter, and whatever's left over, that's your answer. So in this case, it was 3. How about the next one? Again, we're going to ignore plus 1. So I'm gonna write again more stuff that's like not really right, but this becomes a 3. And in this case, what do we get when we reduce 3 divided by a single x, right? Because one of the x's will cancel top and bottom. 3 divided by x. Okay, this one is not as easy, but we can still do it. X is still really big, like 100 or 1,000 or 1,000,000. 3 divided by 100, 3 divided by 1,000, 3 divided by 1,000,000. These numbers are getting very close to what nice number? They're getting very close to 0, right? 3 divided by 100, 3 divided by 1,000, 3 divided by 1,000,000. And 0 is great because that is where the horizontal asymptote is located, y equals 0. Same game over here. We're going to disregard the plus 1 and cancel. What do we get? 3x. Right, 1x cancels, and there's 1 left over on top. X is going to be really big. 3 times 100, 3 times 1,000, 3 times 1,000,000. What's happening to those numbers? They're going to infinity. 300, 3,000, 3,000,000. So on the one side, we're going to infinity. And if you plug in negative 100 for x, or negative 1,000, or negative 1,000,000, you're going to negative infinity. So no horizontal asymptotes. So it turns out, our big conclusions here, let's start with the last guy. What made it so that there were still x's left on the top? What was true originally? Yeah, the higher power is on top. And anytime the higher power is on top, what's our conclusion about horizontal asymptotes? There's none. Because if there's x's left on top, it's going to infinity or minus infinity, right? Okay, so that's written down. You don't need to write it. In this case, we were going to 0 because there were x's still on the bottom. I don't care how many x's there are. If they're left on the bottom, you're going to 0. So what about the original made that true? That's right. The degree downstairs was more than the degree upstairs. So when we canceled, we still had x's left in the bottom. So here's our conclusion. Anytime the degree downstairs is more than the degree upstairs, horizontal asymptote is always, always, always y equals 0. The first one is the trickiest one. That 3 seems to come out of left field. Where did the 3 come from? Why was it 3? Because it was 9 divided by 3. But what made it so that we had to pay attention to the 9 and the 3 here, whereas in the other two, the 9 and the 3 were irrelevant? The degree was the same, right? And if the degree is the same, that's the one kind of magic case where, oh, the x's all cancel and you're just left with those coefficients. And so we have a sort of fancy way to write that. Let's read number 4 here. If the degree of the numerator is less, which means there's more x's left on the bottom, then y equals 0. Anytime you have x's left on the bottom, asymptote is y equals 0. If the degree of the numerator equals the degree of the denominator, then we're looking at those numbers in the front, the leading coefficients. So it's written here y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. You just need to look at the numbers that are leading coefficients and divide. And then finally, the last case, if the numerator has a degree greater than the denominator, then when I cancel, there's still x's left on top. No asymptotes if there's x's left on top. Okay, so let's move on to the next page. We're going to take a look at 7 here. Okay, so just to let you know what the rest of today's class is going to look like, because again, we're doing kind of an audible. We don't normally do things the way like we're doing today. We are going to do this one problem together, even though it's only one problem left. It's going to take a long time. This is a hard problem to graph a rational function. And then at right around 2 o'clock, you guys are going to fill in an evaluation of this course and of my role in this course. Another person is going to come in and proctor that evaluation, and she'll give you instructions. All right, so that's going to happen for the last 10 minutes of our class. I suspect we're going to finish this and not have a whole heck of a lot of time after we finish this one. So the plan is, like I said, we're just doing part of what I intended to do today. We're just doing part of that today. So when we come back in on Friday, there's one other graph on this page that we will do together on Friday to remind us of this big process we're about to do now. And then you'll have almost all of Friday to do the group activities. Trust me, you're going to need it, because in the group activities, I think there's like 9 of these problems, and they're all time consuming. Okay, let's give this a shot. We're going to try to graph this thing, more complicated than anything we have graphed to date. Personally, I like to start with the asymptotes because that begins to develop a shell up on the graph paper. So let's think about vertical asymptotes. Remember, vertical asymptotes happen when you have the denominator equaling 0. Problems in the bottom, right? You can't divide by 0. So we set that denominator equal to 0. You could add 9 to both sides. I think that's risky. It's not wrong, but I think it's risky. Safer is to factor. How does it factor? X plus 3x minus 3. And so what are the equations of our vertical asymptotes? Yeah, x is negative 3 and x is positive 3. All right. At the start of today, we talked about holes appearing. And remember, the holes appeared when we were able to cancel factors from the denominator. But look at the numerator, it's just 2x squared. There's nothing that's going to get canceled. If something were going to get canceled and get a hole, this would be the time we would see it. It's when we would cancel. Okay, so we've got our vertical asymptotes, and like I said, I like to record those things on the graph. So x equals negative 3, I'm putting a dotted line. Go ahead and do a dotted line right there at negative 3, and another dotted line at positive 3. Okay, next thing we're going to do is calculate horizontal asymptotes. This was the last thing we just did. This is the case where we just need to look at the highest power on top and the highest power on the bottom and make a conclusion. Where's the highest power in this case? It's a tie, right? They're both equal. Sometimes highest power on top, sometimes the highest power on the bottom. They each have their own conclusions. We just talked about them. This is a tie, and a tie has its own conclusions. For me, I think about, okay, the minus 9 is irrelevant. And if I'm allowed to get rid of that minus 9, now what cancels? X squared and x squared. And so what's the answer? 2. That's where the horizontal asymptote is. But make sure that you write it as an equation. It is something equal to 2. It is y. It is a horizontal line at y equals 2. And for what it's worth, when I canceled, I'll get rid of this in a second. So we ignored the minus 9. Then we canceled the x squareds and we just got 2. But you don't even have to memorize that it's, oh, for horizontal, it's always a y equals. Look, f of x, what is another name for f of x? Is y. So like it's sitting there, right? It says y equals 2. It's not like out of left field. What's that? We ignored the 9 because if x is enormous, which is what we're talking about for horizontal asymptotes, then x squared minus 9 is pretty much x squared. Subtracting 9 from this massive number doesn't have much impact. Yeah, so it's not like algebraically, you can't just ignore the minus 9, but because we're all friends here. Okay, all right, draw a horizontal line at y equals 2, dotted line, wrong color. Okay, so we've got our shell up on the board. We've got all the horizontal asymptotes and the vertical asymptotes. Let's start getting some points, some real concrete points here. We're going to start with the Y-intercept. which means we let what equal what? Let x equal 0. Got your formula. Everything's going to go back to that original. So this is really saying find f of 0, right? So we just get 2 times 0 squared over 0 squared minus 9. What does that equal to? Yeah, this is a 0 over negative 9, which is really 0. Yeah, okay. So this means that we have coordinates. How much was the x that we started with? 0. What was the y that we ended with? Also 0, and that is a point right there. Okay, we did the y-intercept. Let's find the x-intercepts. Let what equal what? Y equals 0. Which means we're writing an equation going back to that original thing. So instead of f of x, what are we putting? 0. So 0 equals 2x squared over x squared minus 9. Yeah, that's it. Okay, we said this last time. We have a fraction equaling 0. Which part is the important part to make a fraction equal 0? The denominator? The numerator. How do you make a fraction equal to 0? It's the numerator, it's the top, right? You have 0 pieces of apple pie out of 8, right? You have nothing, 0 out of 8. So, sort of surprising, but we completely ignore the bottom and we just focus on making the top equal to 0. Okay, you can do algebra if you want. There's only one answer to this equation. What is it? 0. So x equals 0. Which means that we have coordinates. How much is the x that we found? 0. How much was the y that we started with? 0. So sort of one of the fluky cases where the y-intercept that we first plotted happens to be exactly the same as the x-intercept that we just discovered. Sadly, it means we don't get any new information. So the only x-intercept is the same as the y-intercept. I'll sort of put blue and green right on top of each other there. Okay, now I'm going to draw some stuff here, which you're not going to draw. So let's go here. All right, take a look at the far left. I need my graph to get really close to the dotted horizontal asymptote. It's got two choices. It can either be really close and above or really close and below. We have to do work to figure out which one it is. It should not be obvious which one it is. In terms of this dotted vertical line at x equals -3, I need to get really close to it. I need to go up to infinity, possibly this, or down to -infinity, possibly this. But actually, we could have had some kind of like mixing and matching. Maybe it was this, where it was like above the asymptote, and then it decides to go down to -infinity. And the diagram's already cluttered, but there's a corresponding one that started below the horizontal line and then eventually went up, right? You see there's like a bunch of possibilities there. So we got to figure out which one it is. In between the that vertical asymptote and the x-intercept, there are choices. Either it starts down at -infinity and then comes up to the asymptote, or to the intercept, I should say, or it starts above and hits the intercept. We got to do work to figure out which one it is, right? Could be either one. Notice the top one goes right through that horizontal asymptote. See that? The top thing that we just drew goes right through the horizontal asymptote. Common misconception is that graphs are not allowed to hit their horizontal asymptotes. That is not true. Graph cannot hit the vertical asymptote because the vertical asymptote represents a tremendous problem that we cannot fix. Horizontal asymptote is only relevant at the far right and at the far left. And the horizontal asymptote has no say in the matter in between, okay? So don't get distracted and think it can't hit. Okay, so we got to figure out which it is there. It could continue up that way. It could continue down this way. It could do something where it's down and then it hits and then it goes down again. Lots of possibilities. And then the same kind of thing on this side. Maybe it's that. Maybe it's that. I don't know. So we need one more tool to figure out which of all of these choices it is. Fortunately, the tool is a simple one. So I'm going to get rid of all this stuff. Okay, so here we go. In order to decide whether it was like this kind of thing or this kind of thing, all we're going to do is pick an x value someplace out there to the left of that vertical line and find the y value. If I just had one more point, like if this point were on the graph, divide that, okay, well, I guess it was that one, right? Or if this point down here were on the graph, oh, okay, I guess it was that one. So just one more point is going to get us this information that we need. And the same kind of thing in between the asymptote and the zero and the x-intercept. If this were a point on the graph, I'd say, oh, okay, I get it. It wasn't, apparently it wasn't that, because that would not have hit this point. So we just got to pick points. And the points you got to pick live between vertical asymptotes and x-intercepts. So let's give it a shot. All right, I'm going to pick a point out here someplace, anywhere to the left of -3. -5 is staring at me. I'm going to pick that one, okay? So we're going to pick -5. We're going to go up here and say, okay, how much is f of -5? So we're plugging into the top and the bottom. 2 times -5 squared over -5 squared minus 9. Upstairs, what is it? 50. Don't do 2 times -5. You don't get to do that first. You got to square first. Downstairs, 25 minus 9, 16 is good. 50 over 16 is approximately 3. To be honest, it hardly matters what it's exactly equal to. I just need a rough sense. It's around 3, okay? Which means I've got a point here. What, comma, what? -5, comma, 3 point something I don't care about. So we're just going to plot that point. -5, 3, and change right there. There we go. We know which one of the two pieces out here on the left it was. Did it start above and curve up, or did it start below and curve down? Above and curve up. And with that one little dot, we get to say it's that. And in fact, we actually could have gotten away without saying the dot in this case, because look, if it had been this, what would we have discovered earlier in this problem? An x-intercept. We didn't. We found all the x-intercepts, and that was not one of them. So it for sure could not have possibly come down and hit this x-axis out here. Okay, let's pick another number here in between. Let's do something in between -3 and 0, maybe -1. So f of -1 equals, okay, upstairs, what do we get? 2 times +1 is +2 there, over downstairs, -8. Everybody buy it? Yeah. And so we're going to plot that point. -1, comma, -1/4. -1, -1/4, somewhere around there. And that right there, that one little dot gives me a lot of information. Was it this, or was it that? That's the bottom one, because I got to hit the dot, right? So we draw the bottom one. Hits the dot, hits the x-axis at the origin. And now we play the same game on the other side. It's either going to continue. I'll draw two things. We drew these before. It either continues or decides to bounce. And we just need one more point to decide which of those options it is, right? So we pick another point. We picked -1 before. Can we just pick 1? Okay, so we're plugging 1 again into the original upstairs. Yeah, Upstairs is 2, over, downstairs, -8. So now we get a new point at 1, comma, -1/4. So we plot that new point. That guy. Which means this has to hit the origin and then do what? Has to bounce. Gotta hit there. And I know it's got to get close to the vertical asymptote. Okay, and then one more point is going to do it. Anything bigger than 3. We did -5 before. How about 5 again? So f of 5. Squeeze it in here. Upstairs. 50. Downstairs. 16. Well, that looks familiar. 50 over 16. And so you plot that point at 5, comma, it's a little over 3. 5, comma, a little over 3. See if you can draw that last branch right there. And we get that. What kind of symmetry does this graph have? Over the y-axis, right? Got a name for that. We called that an even function, symmetric over the y-axis. Okay, so like I said, we're gonna do the evaluations in just a minute. We're gonna pause right there. I know it's a lot. I'm also telling you there's no homework assigned on this tonight. We're gonna do one more of these together Friday, and then you'll get lots of practice, and then over the weekend you get to do the homework.